This is joint work with Ramona Caceres at MIT Lincoln Labs, and I'll be talking about a task-driven approach to timescale detection in dynamic networks. So what's the question? There it is. It's very cut off, but OK. We're given as input a raw dynamic network, which consists of a stream of time-stamped edges, which you can see in the bottom row here. And for any, or at least many, data mining tasks, one of the first things you need to choose is a bin size, or what I'll call a window size, where all edges that occur within that bin will be placed into one graph, and then you'll get a sequence of graphs, as you can see in the second and third rows there. Now, if your bin size is too big at the top, then you lose all temporal information, which you'd like to take advantage of. On the other hand, if your bin size is too small at the bottom, then there's going to be lots of spurious correlations, noise, and you don't get to see the effect of the changing dynamics of this dynamic network like you see in the the middle rows here. So the question is how to find this window size. There we go. OK, this is really cut off. I don't know what's happening with this aspect ratio. So pretend that there's words below the screen. So previous work. So one thing that you could do is you could take a look at a time series related to your sequence of graphs. You could look at some specific metric, like the number of triangles. And that produces a time series, one for each in the sequence of graphs. And then you could use that to find a good window size. And in many cases, that's a great approach. But it's not necessarily clear which metric should you choose. Should you look at triangle density? Should you look at, for example, the exponent you find of the degree distribution using a power law, et cetera, et cetera? So one way to avoid that is to use kind of parameter-free heuristics that don't require a metric. These have the advantage that you don't have to choose anything, but they have the disadvantage that I'll get to more in a little bit, the fact that this problem of finding the right window size is task dependent, by which I mean if you have some task you want to accomplish, say, for example, predicting new edges or predicting new attributes, which I'll focus on, you're going to want a different window size for each of those tasks. So if I use a parameter-free heuristic, I'm not going to capture that. And finally, there are task-dependent methods available, but to the best of my knowledge anyway, they fall basically under two categories. One is within a given paper, there'll be some very fancy algorithm that you guys out here will have come up with. And part of that fancy algorithm is some method of finding the right window size for your project. But this is specific to your algorithm. And the other thing that's very popular is to choose a window size that's just natural. For example, if you're talking about people, you'll choose a day or a week, depending on the context. So this is nice, and it's often very helpful. But we have to redo this every time we have a new algorithm, and that's not great. So what this work does is avoid all of that while simultaneously having an automatic way to adapt to any task that you actually want to accomplish, using it as a black box. And we can do this in both kind of offline settings where time is not the biggest factor, and online settings where you have to be very quick. And we show that this approach, at least usually, performs better than some of these other techniques. And it may come as a bit of a surprise, but prior to this, no one has actually directly compared two different windowing algorithms to each other. How well they do do they do compared to each other? Well, no one knew. So part of this was actually writing down a procedure for testing these out. So I did something. Okay. Okay, that helps a little bit. So our approach is very simple. Once we're given a task that we want to accomplish, whether it's predicting new lengths or predicting new attribute values or what have you, we start with our raw network you see in the top left. This will be a training data. You get the time-stamped edges up to the present day. And for each window size W, we're going to bin it at that size and feed it to whatever algorithm you're using for the task you actually want to accomplish. That task algorithm will output something, and then we can measure its quality because we have training data. And that quality will become the score for W. So the window size that we should choose is just the one with the highest score. And just in a little more detail, what does this black box look like? In this talk, I'm only going to be talking about link and attribute prediction, but you can imagine any task you can possibly come up with. So you have some specific algorithm for that task, and there's numerous algorithms for link and attribute prediction, as well as many different ways to measure the quality, for example, the area under the precision recall curve. But whatever algorithm you want to accomplish and whatever quality you want, you put those in. And we have training data so we can actually measure. And I promised that I would talk about the dependency on the task, that we couldn't find a window size for every, that works well for every different task. And this is kind of the summary of why that's the case. If you score every window size for a number of different data sets, both in terms of quality in terms of link prediction and quality in terms of attribute prediction, and look at the correlation between those two variables, you should be able to use one as a proxy for the other if they're highly correlated. That means you only need one window size. But that's not the case. You either get no correlation whatsoever or actually negative correlation. A good window size for attribute prediction is exactly a bad window size for link prediction. Okay. So I'm already running out of time. So very quickly, in the online setting, we can't test every window size in order to make predictions. So instead, when a new graph comes in, we're going to only test a few window sizes, namely the ones that are doing very well, the top scores, and the ones that we don't know very much about. So here, we had no scores so far for a window size of 3, because we only previously had 3 graphs to work with. And now we can test it out. We can find the average score so far. And we're going to choose the highest average score as the window size that we want. And when this is weighted by the how recently we accumulated this score, this is the method that tests the best. That is, for example, in this online framework of link prediction, the windowing algorithm that performs the best overall is this method compared to a bunch of others. And this holds this true for attribute prediction as well, which has even more windowing algorithms you can try. So let me just wrap up by concluding that our approach appears to be necessary in so much as that windowing needs to be task dependent. So we kind of are forced to use this approach. And if we're forced to use this approach, we end up getting relatively good results. And even if you hate this approach, you think you have an algorithm that's leagues better than this very simple one, you can test out your windowing algorithm against this one to just see if the numbers are better or not. So this is kind of initial work. There's much more work to be done, which is that the downside to this approach is that we're running this big black box multiple times. And if it's an expensive black box, then you'll take a long time to come up with a good window size. So we are currently not sure about how to test fewer numbers of window sizes, meaning fewer runs of this big black box, or finding ways to approximate the scores for these window sizes for a given task using faster heuristics. Okay, thanks.